Okay, I will get started then. So, the chapter 20 homework is due today. Tonight, the chapter 21 homework is due on the 11th. The second part 1 is due on the 11th. Part 2 is due on the 18th. We're gonna work our way through chapter 21. We'll start chapter 22, but not next week, but the week after, we will have a review on chapters 19 through 21 and an exam on chapter 21. So we're getting through chapter 21 and I don't think I'm going to tell you today, but we're definitely going to start chapter 22 next week. So, a quick review of Kirchhoff's rules. If you have more complicated circuits, you can't break them down easily into series and parallel phases. And for these circuits, you can use Kirchhoff's rules for useful. The junction rule is a consequence of charge conservation, that the amount of charge going into a junction has to equal the amount of charge going out of a junction. And the loop rule is a consequence of energy conservation, that as you go around the loop, you can't end up with a higher or lower energy than where you started. So the junction rule, at any junction, the current entering the junction must equal the current leaving it. So I1 minus I2 minus I3 equals 0. The loop rule is that as you go around the loop, so this would be epsilon plus delta V between C and D equals 0. Delta V is going to be minus IR. So the electric potential increases from A to B, and then it drops from C to D. That drop is going to be current times resistance. The variables you're solving for are the currents and the resistors. You need as many independent equations as you have variables to solve for, and you'll need both the loop and junction rules. So that was just a quick review of Kirchhoff's rules. Capacitors, as well as resistors, can also be connected in series and in parallel. And have slightly different but similar situations. When capacitors are connected in parallel, the potential difference across each capacitor is the same. And if you want to think about it in an intuitive way, it's like increasing the area of the capacitor. The capacitance increases. So for a capacitor, the equivalent capacitance, the potential difference across each one is the same. Each one holds its own charge. The charges add up. So for capacitors, oh, this is totally dead pen. I wonder if let's see. So for capacitors, equivalent, this is in this is parallel. C1 plus C2 plus C3, or just the sum of the individual capacitances. So they add in parallel as opposed to resistors, which add in series. So the rules sort of switch for capacitors and resistors. So the equivalent capacitance is the sum of the individual capacitance. For series, Capacitors in series don't have the same potential difference across them, but they do end up all carrying the same charge. And the total potential difference is the sum of the potential differences across each one. So capacitors in series have that 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. Sum of 1 over C1. And this gives you the inverse of the capacitance, much like you get the inverse of the resistance. So capacitors in series combine like resistors in parallel and vice versa. So here we have two capacitors connected in parallel across a battery of 9 volts. The total energy stored is 0.0115. Energy stored in a capacitor capacitance 1 is 12 microfarads. What is capacitance 2? Remember that energy stored in a capacitor is 1/2 capacity. 1/2 capacitance times voltage squared. So for this, 1/2 capacitance total times voltage squared is the energy. So the capacitance total is twice the energy over the voltage. So 2 times 0.0115 joules over 9 volts squared. Our total capacitance is 284 microfarads. So this is 0.000284 farads or 284 microfarads. These are in series. So the total capacitance is going to be capacitance 1 plus capacitance 2. So capacitance 1 is just total minus capacitance 1. So 284 microfarads minus 12 microfarads is 272 microfarads. Any questions about that? Here we want to find the equivalent capacitance of these 3 capacitors and the total energy stored if epsilon here is 12 volts. That's a 12-volt battery. So remember, just like with resistors, you could split it into parts and combine them. And capacitors in series, you add the inverses and take the inverse. Capacitors in parallel, you just add. So we can do this in two parts. First, we can combine these two. These are in series, so we have to deal with them as inverses. So that's 1 over 10 microfarads plus 1 over 5 microfarads, all to the -1. The 1/10 plus 1/5, 1 over that, comes out to 3.3 repeating microfarads. And then these are in parallel, so we can just add them. So 20 plus 3.3 repeating gives us 23.3 microfarads for our total capacitance. The energy stored is just 1/2 times the total capacitance times the voltage squared. So 1/2 times 23.3 microfarads times 12 volts gives us 1.68 times 10 to the -3 joules. Because these are microfarads, so that's times 10 to the -6. Any questions about that? Okay. So do capacitors get a larger equivalent capacitance if they are connected in series or in parallel? If you have, I don't know, 10 capacitors and you'd like to create something that acts like something with a much larger capacitance, should you hook them up in series or in parallel? Which way is going to give you the bigger capacitance? Series or parallel? That would work with resistors. It's the other way around. It's in parallel. Because when you put them in parallel, they just add. When you do this, you'll actually always get something smaller than the smallest capacitance.
So
when you do series, you get a smaller capacitance. When you do parallel, you get a bigger capacitance. Same with resistors, except the other way around. Resistors, when you do series, you get a bigger resistance. When you do parallel, you get a smaller resistance. So if I had 10 capacitors that were 10 microfarads, if I put them in parallel, I can get 100 microfarads. If I put them in series, that would be 1 microfarad. I think the easy way to think about it is that parallel is like making the plates bigger, so the capacitance gets bigger. Series is like making the distance between the plates bigger, so the capacitance gets smaller. Okay, we are going to finish 21 today. So if you have a circuit that contains both, that only contains batteries and capacitors, the capacitor is going to charge up almost instantly. But we live in reality, there's always a resistance. The wires have a resistance, something like that. However, if it contains resistors, this isn't the case. So if you have a significant amount of resistance, it can take a while for a capacitor to charge. And so using calculus, basically because capacitance is charge over voltage and resistance is current. And voltage is current times resistance. We can say, and we have a loop like this, we have some fixed. So capacitance is charge over voltage, voltage is current times resistance, and current is the charge dt. you can set up an equation where basically EMF is equal to VQ, VT times resistance plus Q over Q over C. And if you do some calculus, you get Q as a function of time, ends up being capacitance times voltage times 1 minus e to the minus t over tau, where tau equals resistance times capacitance. And if you want, I can go through and do this calculus. Would you like me to or not? Okay. Let me remember how to solve differential equations. Oh no, it's not a hard one. So basically, what? No.
Oh, okay, so then.
No, you just need the this formula.
Oh, okay, so then that's fine.
None of the problems actually require you to do calculus. I can do it to show you, but I'm not going to make you solve the differential equation. No. It's epsilon is equal to how do you, yeah, this is just take me a moment to remember how to. Oh yeah. So you have epsilon equals VQ, VT times R plus 1 over C times Q. And VQ VT times R equals epsilon minus 1 over C Q. Then you integrate both sides. No, that's not right. This is a standard differential equation. I'm forgetting how to do it. Let me write this in like standard form. Something like 1 over C times Q plus R times Q VT plus minus epsilon equals 0. That's, I don't remember. I should know how to do this. It's like a basic first order differential equation, and then it's u minus t over tau as the thing. I am. You can see how I haven't done this in so long. I've forgotten. You're not going to need to do it on the test. Let's just continue. We'll remember how to do it like the end of class, I'm certain, because that's how this sort of thing works. And there's a time constant. It's an exponential decay. up to the target value with the time constant of RC. And the final charge on the capacitor Q is, the capacitance times the voltage. So here's the charge versus time for an RC circuit. Looks like this. Yeah, I can do this for the one that doesn't have a voltage on it. I'm just having trouble remembering how to do it when you have the extra constant added. Not remembering what. Here's charge versus time for an RC circuit. Charge is up. So if a circuit consists of two resistors of 126 ohms and 275 ohms, 182 microfarad capacitor, a switch, and a 3-volt battery in series. Initially, the capacitor is uncharged and the switch is open. At t equals 0, we close the switch. What charge will the capacitor have a long time after the switch is closed? And at what time will the charge of the capacitor be 80% of the value found in part A? So the relevant equation here is that Q as a function of T is capacitance times voltage times 1 minus e to the minus T over tau, where tau, the time constant, is RC. Um,
Or are you just gonna like?
I'm probably just going to describe it. I think for RC stuff, if I ask you like figure out the equivalent capacitance of a circuit or something, I'll draw a picture. But for like this thing, well, on the exam, if I remember correctly, I give something simpler. It's just I tell you that there's a resistor and a capacitor and a battery. And then I think I don't remember exactly what I asked. I think I might just be asking for the time constant. So, if it's relevant, I usually give the picture. I don't recall. I can, it takes a while to draw them. So, I do have pictures for some stuff. I do know that, but I have to go back and look at the exam. It's been a little while. So here's sort of the general gist of it. Charge as a function of time is capacitance times epsilon times 1 minus e to the minus t over tau. So if t becomes very big, e to the minus t over tau goes to 0. So you're just going to get capacitance times the voltage. So 182 microfarads times 3 volts is 546 microcoulombs. That makes sense? Now, if you're looking for what time it's going to be at 80% of the value, well, 80% of the maximum value is going to be 80% of CE. So I'll do 0.8 times CE equals CE here. The CE's cancel. When 0.8 equals 1 times e to the minus t over tau. So 0.2 equals e to the minus t over tau. So t equals minus tau times the natural log of 0.2. Tau is RC. So tau is going to be the resistance, 126 ohms plus 275 ohms, times the capacitance, 182 microfarads. That comes out to 73 milliseconds. So it's what, it comes out to like 401 times 182. And 126 plus 275, 401 times 182. That's and then times 10 to the minus 6. Yeah, it's 0.072982, which rounds to 73 milliseconds. And so the time is going to be negative 73 milliseconds times the natural log of 0.2. The natural log of 0.2 is a negative number. So negative 73 milliseconds times negative 1.61, 118 milliseconds. So it'll take 118 milliseconds to reach 80% charge. Yeah, I think on the test I just asked for the time constant. That tau. Because so that would just be resistance times capacitance. And for a capacitor that's just hooked up to a resistor, current ends up being initial charge, initial voltage over resistance times e to the minus t over tau. That's the current. Well, this is the current in a capacitor that's charging, but it's also the current in the capacitor that's discharging. Yeah, so current is epsilon over r times e to the minus t over tau, because this term goes away, and then you get a factor of 1 over tau times capacitance times epsilon. The capacitance cancels e to the 1 over r. And so you can set up situations where you have one thing with a relatively high resistance that charges a capacitor up slowly. Maybe that's the internal resistance of your battery. And then you have a setup where your capacitor discharges very quickly through something with a low resistance that you want to pump out a lot of energy very quickly, like a flash bulb. So if you've ever used an old camera with a capacitor charged flash bulb, it takes time, like those disposable cameras, you have to hold down the button for the flash. That's charging a capacitor, which then discharges. So here, for example, this is just to sort of think about the circuit. So what current will flow through the circuit immediately after the switch is closed, when the capacitor is going to have maximum current flowing through it. Immediately after the switch is closed, the capacitor is going to act like a short circuit. And a long time after the switch is closed, the capacitor is going to act like it's open. Like this wire is cut. So what do you think the current flowing through this will be immediately after the switch is closed? I'll just go through this. Immediately after the switch is closed, it's as if the capacitor was just connected with a wire. So the total current will be current 1 plus current 2. Here, the voltage across here is just going to be epsilon. The voltage across here is going to be epsilon. So just sort of in general, current total is going to be epsilon over R. And then along here, it's going to be epsilon over R e to the minus t over tau. At time t equals 0, this is just 1. We have 2 epsilon over R. It's as if you just had 2 resistors hooked up in parallel. At time t equals infinity, this goes to 0. And you just get epsilon over R. Does that make sense to you guys? Basically, right away, capacitor acts, just lets current flow through. But after a long time, the charge builds up and it doesn't let current flow through anymore. Here's another situation. So how much current flows? You want to figure out the current that flows through the circuit immediately after the switch is closed, and then a long time after the switch is closed. So here, this is just a basic RC circuit with a equivalent resistance of R over 2. So current The flow through the circuit is going to be epsilon over the total resistance times e to the minus t over tau. So epsilon over r over 2, e to the minus t over tau. So 2 epsilon over r, e to the minus t over tau. Immediately after the switch is closed, epsilon is time is 0. That e to the minus 0 over tau is 1. So that's 2 epsilon over r. A long time after, epsilon e to the minus infinity over tau goes to 0. The whole thing is 0. No current flows. So because there's no route that doesn't pass through the capacitor, no current flows a long time after. So we talk about charging a capacitor. We can also discharge a capacitor. And this is charging a capacitor. Discharge the capacitor. Q of t just equals your initial Q times e to the minus t over tau. Much simpler. The current formula looks the same. Current in both of these ends up being the derivative, which is it looks like something like epsilon over r e to the minus t over tau. In both cases, there's some sign differences, but they're not a big deal. And tau is still r times c. This one I can do the calculus for you because I won't get screwed up by that constant. I think you can just do a substitution of variables and do the integral. That's right. So I could do it afterwards. I don't remember how. Any questions about this? Pretty straightforward. A lot of circuits exist that are designed to charge a capacitor slowly and discharge it quickly. Because often batteries sort of have a limit of how fast they can pump out charge. You could slowly pump out charge to charge a capacitor up, and then quickly discharge it to dump a lot of current out into something, like a flash or a rail gun or whatever. So there are also ammeters and voltmeters. An ammeter is a device for measuring current, and a voltmeter is a device that measures voltage. We've used an ammeter in lab. Today we will use a voltmeter in lab. So an ammeter measures current, a voltmeter measures voltage. For an ammeter, the current has to flow through it. You can't measure current from the outside. Actually, you can, but that involves a more expensive device that we don't have. There are things called clamp ammeters that use a magnetic effect to measure the current flowing through a wire. But in general, the current in the circuit has to flow through the ammeter. Therefore, the ammeter should have as low a resistance as possible for the least possible disturbance. So if you want to measure the current in the circuit between A and B, you have to put the ammeter in the circuit. A voltmeter, on the other hand, measures the potential drop between 2 points in the circuit. Therefore, it is connected in parallel and should have as large a resistance as possible. When you're measuring voltage, you hook up in parallel with what you're measuring. So if you want to measure the voltage drop along this resistor, you hook the voltmeter to either side of it in parallel. And ideally, your voltmeter doesn't allow any current to flow through itself. So it should have as large a resistance as possible. So that's the end of chapter 21. Electric current is the flow of electric charge. The unit for electric current is the ampere. 1 ampere is 1 coulomb per second. A battery uses chemical reactions to maintain a potential difference between its terminals. Potential difference between battery terminals in ideal conditions is the EMF, which is electromotive force, which is not a force. It's a potential difference. Sometimes things have terrible names. The work done by a battery moving charge around the circuit is the charge moved times the EMF. The direction of current is the direction that positive charges would move, even though the actual things moving are negative charges, because joy. Ohm's law is that for resistor, an ohmic device, voltage equals current times resistance. Resistance can be related to resistivity, where the resistance of like a wire is the resistivity of the material it's made of times its length divided by its cross-sectional area. Generally, resistivity will increase with temperature. In certain materials, the resistance of it are superconductors, and their resistance drops suddenly to 0 at a critical temperature, T critical. They have other limits, but they have 0 resistance. The power in an electric circuit is current times voltage. If the material obeys Ohm's law, power equals IR squared, or V squared over R. The energy equivalent of 1 kilowatt hour is 3.6 times 10 to the 6 joules. For resistors in series, you add the resistance, R1 plus R2 plus R3. For resistors in parallel, you add the inverse of the resistance is the sum of the inverses. It's the harmonic sum. You want to use a fancy term for it. The 1 over R equivalent is the sum of 1 over R. The junction rule is that all current that enters a junction also has to leave it. The loop rule is the algebraic sum of all potential charges around a closed loop needs to be 0. For capacitors, it's the other way around. Capacitors connected in parallel add their capacitance. And capacitors connected in series, the equivalent capacitance for capacitors connected in series is 1 over C1 plus 1 over C2 plus 1 over C3. For charging a capacitor, charge over time is capacitance times voltage times 1 minus e to the minus t over tau. And current over time is epsilon over r times e to the minus t over tau. Discharging a capacitor, charge is q e to the minus t over tau. An ammeter measures current. It's connected in series. Resistance should be as small as possible. A voltmeter measures voltage and is connected in parallel. Resistance should be as large as possible. So that's the end of chapter 21. Let's see. Let's start chapter 22. So chapter 22 is about magnetism. So we covered electricity and moving electricity. And now I will cover a little bit about magnetism. Unless there's any questions about the stuff we went over in chapter 21. Yeah, we're gonna have a review day on the Monday of the week of the exam, and then the exam on the Wednesday. And I'll try and add more circuit diagrams to the exam if they're not there. Now that you mentioned it. Shouldn't be that hard to make. It may be a bit sketchy. So, magnetic field. We're going to talk about the magnetic field. We'll talk about the magnetic force on moving charges, the motion of charged particles in a magnetic field, the magnetic force exerted on a current carrying wire, loops of current and magnetic torque, electric currents, magnetic fields, and Ampere's law, and then current loops in solenoids and magnetism in matter. So, there's an electric field. There's a force between things with a static electric charge. Positive charges attract, negative charges repel. Permanent bar magnets, if I dig out some bar magnets, they have two poles, two north poles repel, a north and a south pole will attract. Like poles repel, opposite poles attract. But you'll never find a magnetic pole on its own. There are no magnetic monopoles. Even if there was a room labeled monopole storage in the physics building when I went to college. That was a joke. So if you break a permanent magnet in half, each half will have two poles. So unlike the electric field, which starts at positive charges and ends at negative charges, the magnetic field actually continues through a permanent magnet. It makes loops. So we can visualize the magnetic field with magnetic field lines similar to the electric field. You can sort of draw them in the direction a compass would point. Because a compass is just a magnet that identifies direction of a magnetic field. They would go out of the north magnetic pole and into the south magnetic pole. The compass will point towards the south magnetic pole of a magnet. That's because the magnetic poles of a magnet are defined by which direction they point in the Earth's magnetic field. So the north magnetic pole of Earth is actually a south magnetic pole. So if you go to the north, the magnetic pole of Earth that's in the north of here, I don't know which direction I'm pointing. That pole, the one up in the Arctic, is a south magnetic pole. And the one in the Antarctic is a north magnetic pole. But that's just because we've named the magnets by what direction they point. If you have iron filings and are allowed to orient themselves around the magnet, they'll follow the field lines. So if you have little bits of iron that they will line up along the lines of the field and follow along the field lines as they get magnetized. And by definition, magnetic field lines exit from the north pole of a magnet and enter at the south pole. And they can't cross, just like electric fields cannot. But you can set up a magnet so one side has a more intense magnetic field than the other. Here's an example. So a lot of fridge magnets are actually set up like this way. The flat ones. They're set up with magnetic stripes. So that one side, all the magnetic fields basically cancel out, and the other side, you get a much stronger magnetic field. Though it's not always pointing in the same direction, but you get more intense magnetic fields on one side than the other. The Earth magnetic field resembles that of a bar magnet. but since the north poles of the compass needle is pointing towards the north, the magnetic pole there is actually a south pole. So here we have a compass. It is pointing this way towards this magnet. Is pole 1 on this magnet a north pole or a south pole? So the compass is pointing towards pole 2. So is pole 1 a north pole or a south pole? So compasses point towards south magnetic poles. Yeah, so if you have a compass, the direction it points will be magnetic north. What it is pointing towards is the south magnetic pole of the Earth. If inside the Earth there was a giant bar magnet, we would call the pole that a compass points at the south pole. What?
It's always pointed at the sun.
Yeah, so here it's pointed at the south pole of this magnet, which is 2. So the other pole is a north pole. So pole 1 is a north pole.
Opposite.
Yeah. And actually, if you stuck it in here, oh no, it's still pointing. It'll keep pointing it. You put it in the middle, it'll point towards 1 because it's following the magnetic field along the line.
So at the end of the day, whenever the arrow is pointing towards the sun.
Yeah, from the outside, yeah. Because the actual magnetic field lines form like a loop. So they're going in and go out and around. Okay. And they're a little weird inside. The other way to think about it is that the arrow on the compass is the north pole of the compass magnet, so it is attracted to the south pole of the other magnet. Okay, and then I'll go over this. So it turns out if you have a charge that's moving through a magnetic field, it experiences a force. Because it turns out the electric field and the magnetic field are related to each other. And that force has a magnitude that is proportional to the charge. The bigger the charge, the bigger the force is. Proportional to the magnetic field. The bigger the magnetic field is, the bigger the force is. And also proportional to the speed that it is moving. So the force on a charge moving through a field is charge times velocity times the magnetic field times the sine of the angle between the velocity and the magnetic field. Strictly speaking, it is what's called a cross product. So this is an experimental result. If I fire some charges into a magnetic field, they're going to bend. I'll see them experiencing a force. And it will have this magnitude. It's not a consequence of anything we've learned so far. This is something we observe. This is actually how we define the strength of a magnetic field. So magnetic field is the force on a moving charge divided by the charge times the velocity times the sine of the angle. And the unit, it's force over charge times velocity, which ends up being newtons over amps times meters, which is a unit called 1 Tesla. And 1 Tesla is a really big magnetic field. Like the Earth's magnetic field is something like 10 to the minus 4 Tesla, something like that. I don't remember. It's like a Gauss. Gauss is like 10 to the minus 4. Yeah, I think around 10 to the minus 4 Tesla. So, you know, one Tesla magnet is a dangerous thing. If one Tesla permanent magnet will apply so much force to other things. Now, the other thing is that the direction of this force is not, it's a cross product. It ends up being at right angles to both the force and the magnetic field. And you can figure out what direction it is by taking your right hand and you point your fingers in the direction of the velocity and you bend them in the direction of the magnetic field, and your thumb at right angles to both sets of your fingers will point in the direction of the force. That is because that force is charge times velocity cross magnetic field. That is the force you'd have on a positive charge. A negative charge would be in the opposite direction. So this relationship between the free vectors, magnetic field, velocity, and force can also be written as a vector cross product. Force is charge times velocity cross magnetic field. That's where the sign comes from. Cross products give you a sign. I'm going to stop there for today. We'll go over this again next time, and we can do the lab.